Welcome to our presentation of the Distributed Kingdom Hybrid Communication System. This design aims to tackle the challenge of long-distance communication in a medieval context, and we draw inspiration to actually solve this design challenge from historical systems like Roman beacon networks, Native American drum communications, and semaphore flags used by Napoleon's army or by the World War I navies before the advent and creation of radio systems. Each of these systems was innovative for its time, and our design tries to combine all these ideas into a hybrid network to ensure scalability, reliability, and security. This layered approach adapts to varying environmental conditions and security needs while we still address the limitations of this pre-industrial technology. So to start, let's actually look at how our physical communication system is going to work. As you can see, we have three different primary communication methods: beacon towers, semaphore flags, and drums. Each method complements the other to ensure adaptability. Beacon towers are used at night, with binary signals being encoded by the fire being lit or unlit. We also have this shutter mechanism, which will actually correspond to the fire being lit or unlit. When the shutter is on, we won't be able to see the fire, so that counts as unlit. And when we pull the shutter to the side, the fire is visible, and that counts as lit. Semaphore flags are used during the day, with the flag position representing binary states, up being 1, down being 0. Finally, we have our drum system, which serves as a backup system during bad weather or when the other methods fail, using a loud beat to represent 1 and a soft beat to represent 0. We also have the following network topology. Our network uses a hierarchical topology to manage message propagation efficiently. At the middle or at the top, you can think of the king node, which will communicate with our different regional nodes. These nodes then relay the messages to local nodes, which are closer to villages or outposts in our kingdom. We also have these redundancy paths, as represented by the dotted lines, built into our system to ensure reliability in case of node failure. For example, if the message propagated by the king doesn't reach region 1, but it is able to reach region 4 or region 2, because of the backup network connection, the message can still reach region 1. Same thing when we look at a region to local node connection. If region 1 propagates a message that node 2 misses, but node 12 or node 1 receives it, they can propagate that message over to node 2 and it still receives our message. Another big consideration that we had to have was actually synchronizing all our different regions to ensure we had clear and synchronized communication. So to do this, our system uses a robust signaling scheme with start and end signals, message headers, and predefined codes. Timing protocols are critical, and we actually made sure that each binary signal was transmitted over a fixed interval of 2 seconds. Finally, synchronization across our nodes is achieved in two ways: sundials and water clocks. At sunrise, signals are sent out to mark the start of the day, making sure that all our regions become aligned. Periodic synchronization every 3 hours will ensure the timing stays consistent throughout the network. We'll primarily rely on the sundial using the shadow cast by dial to stay synchronized in time. However, our water clock design, which we will place in all the key areas in our network and has an equal rate of water flow, will ensure that even if the sundial fails, regions can still stay synchronized by using the water clock. Now, to show the consistency protocol, we can look at the message propagation flow. To ensure the messages are delivered consistently, we use a wave-like propagation method, where each node relays the message it receives to its neighbors. As always, the redundancy paths ensure delivery even if a node fails. We also have acknowledgement chains to confirm message delivery, with nodes sending acknowledgements, which we refer to as ACKs, back to the sender. If errors are detected, retransmission and synchronization protocols help recover lost and delayed messages. We also have to consider elections in our design. In a decentralized network, leadership transitions have to be managed dynamically. So our election protocol is triggered when a leader is unavailable or unresponsive. Nodes will nominate candidates, and votes are tallied to elect new leaders. We have fault tolerance mechanisms handle scenarios where the election is fails, ensuring neighbor regions temporarily manage operations. Let's look at an example trigger. So let's say region 3 becomes unresponsive. Local nodes will detect the failure and initiate our election protocol. The eligible nodes in region 3 will nominate themselves. Let's say region 3 node 6 and region 3 node 7. Then all the nodes eligible to vote will broadcast their votes. As you can see, R3N6 will vote for R3N6. It's going to vote for itself. And same thing with R3N7. So our deciding vote comes from R3N8, which will ultimately vote, as you can see, we caught a mistake here, will ultimately vote for R3N6. And as a result, R3N6 becomes the new regional leader, and it'll broadcast its new role to Region 3 and neighboring regions. There are advantages and several disadvantages that we need to highlight. It is a highly reliable design because of our hybrid communication system and redundancy in the paths. We can adapt to change to conditions. We have robust error handling mechanisms and scalable across large territories. However, there are limitations, such as weather dependency for beacons and flags, increased latency due to the redundancy in our network, and we require significant infrastructure for building and maintaining our network. Finally, we have a security protocol, which is highlighted in this section here. Our network implements security protocols tailored to the sensitivity of messages. For low security decrees, we use a fan-out propagation with beacons and flags. Medium security involves controlled propagation with acknowledgements to specific nodes. And finally, for high security commands, we use point-to-point communication with trusted nodes, avoiding methods like beacons to reduce interception risk. So in conclusion, the distributed kingdom hybrid communication system that we've designed offers a scalable, secure, and efficient solution for long-distance communication in the medieval context. While there are limitations, such as weather dependency, infrastructure challenges, the design ensures adaptability and reliability across various scenarios. Finally, there are ethical considerations, such as operator strain and message interception risks, and these can be addressed and improved upon in future iterations of this network. Overall, this design builds on historical methods while addressing the unique challenges of actually creating a functioning medieval communication network. Thanks for tuning in.